Find for this FDP. So yeah. So my name is Narayanan. So I'm a STEM professor from Department of Electronics and Communication Engineering from IIIT Bangalore. And today I will be delivering a session for the FDP. The topic will be from sensor design to efficient readouts, challenges, and solutions in sensor measurements. So the main focus will be on capacitive-based sensor, and I'll try to align the talk towards the biomedical application, right? Yeah. So before presenting this session or this topic, let me give an overview of my research. So how to, yeah. So let me give an overview of my research. So my area of research is in sensors, measurements, and instrumentation. And the research mainly focus on two verticals. A vertical one is designing a sensor, mainly the sensors which is passive, not active. So I'm the sensor design mainly deal with the capacitive and inductive based sensor. So I have designed a few sensor for liquid level, dual axis inclination, composition measurement. So all these sensors application is in automotive industry and agriculture applications. And apart from that, I have also developed few signal conditioning circuits, which is efficiently measure the changes in capacitance or inductive sensors. So this is the main research area. And truly speaking, I don't have much what we say research experience in biomedical application, but the thing is like whatever I have designed so far in capacitive and inductive sensor all align towards the biomedical application. We can directly apply that sensing design rules directly to these biomedical applications. Right. So let me give some more overview of my research, what I have done so far in the previous 5 years. So this is one important sensor that I have developed. One is sensors for liquid level and inclination estimation. So I have developed both capacitive based and inductive based sensor. So the main objective of the sensor is to measure the level, liquid level. Maybe it may be fuel or water or any other liquid. The inclination of the liquid and the composition of the liquid. So the main application will be in automobiles in fuel sensor. So what is the advantage of using this sensor is that it's a single sensor which can measure all these three parameters, and it has very low cross sensitivity and very high accuracy in measurement. I also developed few inductive based sensors similar to this, which can be directly used for high viscous liquids or the application where the permittivity changes a lot, right? So in addition to that, I have also developed few efficient readout circuits, basically for reading the capacitance or inductance of the sensor which I have developed, basically capacitance to time converters and inductance to digital converters and so on. Apart from this, I also have expertise in designing sensors for sensors and sensor systems for automotive industry, especially as you can see here, one sensor which we have developed, which is steering wheel hand position sensor. So there we have introduced a new capacity sensor modality, that is pi model capacity sensor, and also I have developed few inductive based angle sensor. So these are the outcomes of this research. So this is the overview of my research. So if you can see that most of the research area fully align over the automotive or agriculture industry, right? Yeah. So coming to today's session, so I will deal with the sensor design and mainly for capacitive based sensor, and I'll try to align that with the biomedical applications. So let us start with the different sensor modalities which exist in biomedical applications. So here we can see 5 different modalities of sensing: resistive, capacitive, piezoelectric, inductive, and optical. And these all sensor modalities are directly used, heavily used for wearable sensor, wearable based biomedical applications. So apart from this, we have semiconductor based and based sensors, which are also being used in biomedical application. So we have resistive based sensors where it's equivalent to a variable resistor. Whenever there is a measurand which need to be measured, the resistance of that particular sensor varies, right? For example, as shown here, it's like a piezoresistive sensor. Whenever there is a force applied, there'll be a change in the resistance accordingly. There'll be maybe due to the change in the conductivity. Similarly, we have capacitive sensors. The main peculiarity of capacitive sensor is like it has two conductive metallic electrodes, as shown here. Yeah, so as shown here. So whenever there is a change in the measurement, for example, if I apply force or there is any displacement in this electrode, there will be corresponding change in the value of D, that is the distance. So accordingly, the force is converted to the capacitance. So the same is the process when there is any permittivity or the level of the material within the capacitance and so on. So that is the basic principle used in capacitive sensor. The third modality is piezoelectric type of sensors. So again, it uses piezoelectric material. Whenever there is some application of force, there will be the voltage drop build or voltage potential drop across this material, and that will be proportional or a function of the measurand, for example, the force itself. Similarly, we have inductive sensor. So you could see here some spiral metallic coil. So this is a planar coil. So it forms an inductor. So whenever there is like a movement or when there is a bend in the inductive coil, there will be a corresponding change in the inductance. Basically, there will be some change in the magnetic field, right? And we have optical type of sensor where there is any change in the refraction or refraction of the light incident, and this light incident on the photo detector can be used for measuring the measurand. So these are the basic principles, five or basic modalities being highly explored in designing the sensor for biomedical application. So in this talk, we'll completely align with the or deal with the capacitive sensor and its design, right? So let us come to the capacity sensors and what all sort of capacity sensors or what sort of technologies of capacity sensor are used in biomedical applications. So similar to the previous one, the capacity sensors are will align in any one of this bucket. Like it may be used as a coupling capacitor type, or it may be used as a parallel plate type, or it may be used as a coplanar type of capacity sensor. So what is a coupling capacitor type capacity sensor? Is like a single metallic plate. So consider this is as a human body or skin, and I have a metallic electrode here. So any signal arising from body or any change in the ionic concentration here can be detected through this metallic coupling plate. So this is equivalent to a coupling capacitor here, as shown here. So any change in the or the signals from the human body is coupled to the outside world. So though the signal is very low, we can pre-amplify and use the signal for various applications like ECG or EEG monitoring and so on. So this is one method or type of capacity sensor used in biomedical, and we can collectively call it as a coupling capacitor type capacitive sensors, right? And as I told, the application is like for non-contact ECG, EEG monitoring, or for proximity wearable diagnostics. Like for example, most of the wearable sensors need to be in close proximity to the human body. So whenever there is any change or any loose contact with the surface, we can easily debug that, right? That proximity using the change in these capacitors. So all those applications align with this coupling capacitor type capacity sensor. The next one is the other method used, or the other topology used is a parallel plate type. So as shown here. So here basically we have two metallic plates as shown here. Two metallic plates, converted capacitive sensor, and usually one metallic plate is fixed to some surface. So for example, this is fixed to surface, and this metallic electrode is fixed to the skin. So whenever there is a movement in this measurand or the item to be measured, for example, if I want to measure the respiratory variation or the movement of the skin, I will connect this metallic electrode to the skin. So what happens between the two plates? I have a capacitance, right? Epsilon A by D. So whenever there is a movement in between the two plate, there will be corresponding change in this capacitance, right? So that we can directly make a function of or proportional to the measurand, which need to be measured, right? So that is the basic principle used in the parallel plate type. So this is the variation of D. We can also have the variation in A in application. So this is another type. So most of the applications like pulse wave monitoring or for respiratory monitoring or even for electronic skin, in all we basically use this parallel plate type capacity sensor, right? So that is a conventional way of measuring the capacitance. Yeah. Now the third type of capacitive sensor is the coplanar, as shown here. So compared to these two, so 1 and 2, here in coplanar, we have both the plates, say plate 1 as well as plate 2, kept over the same plane. So what happens if suppose I apply a voltage across this? So for example, this is plus and minus. So what happens? There will be a field lines from plus to minus this electrode. So these are known as the fringing fields. Okay. So what happens whenever there is there is any object or there is any variation in the epsilon r, there will be a corresponding change in the capacitance, right? So this change in the capacitance is usually used as sensing. Okay. So some of the applications is like to analyze the fat tissue, the concentration of fat tissue beneath the skin, or for detecting the skin hydration, or even to moisture or sweat content over the body. So for all these applications, we use a sort of capacity sensor known as the coplanar type. Now, the mainly used coplanar sensor is an IDE sensor. Right. So what is this IDE sensor is that if I have two metallic plates, two metallic coplanar plates, right? Compared to a parallel plate capacitor, the capacitance of this coplanar plate, say I'll call it as CP, and this is a parallel plate CPL. The capacitance of this value will be very, very less compared to a parallel plate capacitor. And also the sensitivity of the capacitance will be very low. So what happens is that if I use two metallic strips, the variation in the capacitance will be very low in the applications. So we usually use a number of metallic electrodes as shown here. So this is an interdigitated electrodes. So we have more than one electrode. So this will be electrode plus and this will be electrode minus. So compared to this, a single electrode coplanar sensor will have n number of capacitors. So if this is having a capacitance Cp, this will be having an n minus 1 times Cp capacitance, right? So this is the capacitance which is shown here, which is used to measure the respiratory hydration assessment, right? So this is the coplanar type capacitance. So there are plenty of applications where we use the coplanar type capacitance, right? So this is an overview of capacitive sensors which is used in biomedical application, right? So we can design a capacitive sensor easily by simply designing its area and distance between the plate. So it's very straightforward in designing the sensor appropriately for any applications. The only thing that we need to check is like what should be its sensitivity, what should be its resolution. So based on that, we have to carefully design the area, even its type in which we need to align, that's to be parallel or coplanar or and so on, right? So this is the capacitive sensor. But when we design a sensor, especially a capacitive sensor, we need to design in such a way that it won't be affected by the external interferences, right? So if I want to design a sensor like this, a parallel plate capacitor, we'll see what all things or what all non-idealities will affect this sensor and how to overcome that. Fine. So we'll see how a capacitive sensor need to be designed so that we can measure the measurement very accurately, right? So let us see a parallel plate capacitor as shown here. So for an ideal parallel plate capacitor, the capacitance between the two plates is like Cx equal to epsilon A by D, right? Where A is the area of cross section and D is the distance between the these two plates. So between these two plates, right? So when I design or when I try to fabricate such a capacitive sensor, the capacitive sensor will be somewhat like this, right? We will have two PCBs. So rotate. I have a PCB1 here and PCB2. Okay, and this green block is an FR4 or it's a substrate, and this black one is a metallic sheet or metallic plate, right? So when we align these two PCB at a distance D, okay, there will be a capacitance Cx equal to epsilon A by D. So that is a conventional capacitor. Okay, so ideally speaking, these two metallic plate will have a capacitance like this. And whenever there is a movement of this plate or this plate, there will be corresponding change in the capacitance. So that is the ideal case, right? Now, in practical case, let me erase this. Yeah, but in practical case, what happens? So this yellow line is electric field. When I apply a voltage plus minus, these are electric fields. But what happens in a non-ideal case or practical case, what happens? There will be electric fields bulging outside this area, right? This one. So these are again the fringing field. These are also known as the fringing fields. Okay, so what happens if it was a previous case? Say, for example, if it was an ideal case, the electric field lines are correctly perpendicular from the top plate 1 to 2. But what happens in the practical case, there will be fringing field. So the actual capacitance Cx will change. The actual capacitance Cx won't be equal to epsilon A by D, right? So this will be it will be a function of this fringing field. So if I called F as the fringing field, function of that. Won't be a constant depending upon the distance between the two plates or the area of overlap. The intensity of the fringing field will be different, and it creates corresponding change in the capacitance, right? So there will be a lot of error due to this fringing field, right? Now, apart from this, when we see the real environment, there will be plenty of other coming from outside world. For example, there will be interference signals coming from outside trees or any other system. Or maybe like if I bring my hand near to this plate, what happens? There will be corresponding field lines between hand and the metallic plate. So again, this also will create an error. I'll call this error due to the interferences. Okay, so what happened? In effect, the net capacitance won't be equal to epsilon A by D. So there will be a large variation compared to the capacitance value. There will be a large variation, and this variation won't be a constant. It will be always varying. So if I draw if I draw the capacitance versus time, instead of getting a straight line, it will be something like this, depending upon the interferences. So why this effect is this effect creates too much of effect on its capacitance value, right? Cx. So why this effect is very crucial. Answer is that the capacitance value of sensors will be in picofarad. okay, several hundreds of picofarad. And this variation will create a variation of near to 10 to 20 picofarad changes, right? So which means the variation will be of like 10 to 20 percentage variation will be there. So it directly affects the repeatability of the system, right? The effect, it directly affects the repeatability of the sensor, or even the sensitivity also may be affected by this interferences. So this is a very bad design, I would say. It will be a very bad design for a parallel plate capacitive sensor. So how to eliminate the effect of this fringing field and the interference from the outside world? So the simple method is like, we'll have two more metallic plates as shown here. So this is metallic plate 1 and this is metallic plate 2, which is corresponding to the same metallic plate as shown here. This is plate 1 and this plate 2, right? Apart from that, I have added two more plates. You can see here plate 1 here and plate 2 here, which is near to the plate 1, and this is another plate here and a plate here is near to the plate 2. And what I have done is like, we will connect same potential. So I have added a potential plus here and plus minus. The same potential I will apply to this plates. Okay, so these plates, guard plate or ring plate. So we'll connect the direct voltage, same voltage to the guard plate. Okay, so what happens? So let me just erase this. So we have applied the same potential here, plus minus, plus minus. So what happens from this point to this point? We will get electric fields which are perpendicular to the surface, and at the end only fringing fields, okay, which is not required, right? And this fringing field actually affects the capacitance between the two plates. So we have capacitance between these two plates, we have capacitance between these two plates, and we have capacitance between these two plates, right? So what happens? This fringing field affects mainly on this capacitance as well as this capacitance, while this capacitance, which is the capacitance of the sensor, will not be affected by the fringing field, right? So the electrical equivalent will be somewhat like this. So I have our required capacitance, so I'll call it as, okay, and we have some other capacitance, so I'll some CG1 and CG2 corresponding to the capacitance of the guard plates. Okay, so this is CG1 and CG2. Definitely the CG1 and CG2 will vary with respect to the fringing field and the interferences, while it won't affect the capacitance CXY, because this node is connected to this node of this capacitance through a, okay, similarly this node is connected through a buffer, and here also. So even though potentials are same, even though potential here are same, right, these potentials are same, but it is actually physically isolated. So what happens? Any effect of this will won't affect the capacitance Cx. So ideally speaking, we what we'll get, we'll get Cx to be equal to epsilon A by D itself, even though there is fringing field. So this is a better design which helps to eliminate the fringing field, right? Yeah. So so this is a method to overcome the fringing field. And now coming to due to the interferences. So now the two metallic guard plates here to avoid the fringing field, but what to do with the external interferences here? Okay, so even though the effect of this guard signal, the fringing signal is overcome, we have from the outside world. Again, that will definitely affect the capacity. So now also the Cx won't be equal to epsilon A by D when there is some external interferences. So what to do, to how to overcome this effect? So to overcome this effect from the external, what we'll do, we'll one more guard plate over the second layer. So this is metallic plate. Okay, so metallic plate 1 and metallic plate 2. So you could see we have the metallic plate 1 here, metallic plate 2, which corresponds to our the main metallic plates of the capacitive sensor CX. Apart from that, we have the guard plates here, okay, to the fringing field, and we have a metallic plate here. Okay, so this metallic plate again will connect to the same potential plus through the buffer. So what happens? The external field lines will affect the capacitance due to these guard plates, right? The CG1 and CG2 will be affected, while the capacitance between the two plates won't be affected, right? The metallic plate capacitance will be affected by the external plate. So in effect, we are able to eliminate the effect of external interferences. So again, the equivalent circuit will be same as the previous CX, and definitely the CX will be independent of the interferences as well as the fringing field, right? So this is a better design for the capacitive sensor to overcome these two interferences. So these are the top and bottom plate for a parallel plate capacitor, right? So this is in terms of a sensor design, what all things we need to be cautious about while designing the sensor. Now coming to the measurement side, when I use such a sensor, so I have the guard plates on both the top as well as bottom plate, and definitely it avoids the interferences from the external world as well as the fringing field. And I use the same sensor to measure and, for example, displacement or vibration, whatever. And I want to measure this, right? So any change in the capacitance CX, I need to measure so that I can find what is the value of this measurand. Okay, so I need to connect this to a measurement circuit as shown here. Okay, so when I connect to a circuit, what happens is like we have some cables. We need some cables to connect to the measurement circuit, right? So usually in most of the application, if I have a sensor kept here, okay, which is in direct affinity towards the say application, say like I have a human hand and have the sensor, the measurement system will be kept somewhere else, okay, and it need to be connected through a long wire or through long cables. So as shown here. So what happens? These two long cables will have the capacitance, right? Interwire capacitance as shown here. So I'll call this as CC, which corresponds to the cable capacitance. Apart from that, whenever there is any objects or human hand or anything which is coming near to these wires, there will be corresponding change capacitance. So there will be some capacitance, coupling capacitors here as shown here, which will be added to this capacitance. So what happens if I connect this sensor to a measurement circuit through long cable, the output data, which should be proportional to CX, won't be equal to CX. Okay, it will be a function these values. For example, the C1, CC, C2, etc. etc. So what happens again? The capacitance again change and it will affect its repeatability, its accuracy, and so on. So what to do? So how to overcome this? So how to overcome this is like again adding a guard cables, or we'll add a shielded cables. We need to connect the sensor through a cable which is shielded by some metallic plate or metallic mesh as shown here. So this is a normal biaxial cable, or I mean a shielded cable where it is guarded by the metallic mesh, okay, as shown here. So what happens? This is the center metallic wire through which we'll connect to the measurement circuit. And what we'll do, we'll just connect the outer metallic mesh to the ground. So what happens if any interferences come here, it will be directly grounded, right? It will be directly connected to the ground. So it won't affect, right? It won't affect the actual metallic cable which is connected to the measurement circuit. So in effect, what happens? The value which is measured by the circuit will be equal to Cx itself and won't be affected by the outside interferences, or even if there is any movement in the cable, it won't affect the capacitances, right? So that's how we shield the sensor so that it becomes immune to all these non-ionizers, right? So this is the better design, I would say. So I guess it's clear, and we'll see its equivalent. So when we connect a sensor to a measurement circuit through such a shielded cable, it will be something like, okay, so this is our Cx, which is not affected by any of the interferences, and both this node will be connected to a ground through a capacitance due to this capacitance. So when there is a shielded cable here and there is a metallic wire here, between the metallic wire and the shield there will be a capacitance, right? So I'll call this as Cp1, Cp2. Okay, so what is this capacitance? This is the capacitance between the metallic wire to be connected and the shield. Okay, so those are these capacitance, Cp1 and Cp2, okay, to the ground. And these are parasitic capacitance, and the peculiarities of this parasitic capacitance is that it's totally fixed. Okay, it's a fixed capacitance, parasitic capacitance. And the measurement circuit should be in such a way that it measures only the value of Cx, okay, independent of the Cp1 and Cp2. Okay, so we have the shields and all, but the shield will create a parasitic capacitance. So if the measurement circuit is efficient enough to overcome the values of this capacitance, we'll get a very accurate design, right? So this is a capacitive sensor design which we need to keep in mind. Yeah, so the same design we can extend to all the coupling capacitor type or coplanar type capacitive sensor. So as you can see here, instead of having a single metallic plate, we can have guard plates here for the coupling capacitor type, for a parallel type as discussed, and similarly for coplanar type, we have the metal 1 and 2 here, but again it has to be shielded outside, right? So it will lessen the effect from the fringing field from here. So any fringing field from this side will be eliminated, and only the measurand in this can be sensed easily, right? So same approach we can directly apply for the coplanar and coupling capacitor types. So we'll see. So the best approach is for accurate sensing in capacitive sensor design. So I guess it's clear. Should I stop here for any questions? So I guess no. Any questions? Yeah, so I'll go. So please feel free to stop me at any. That's about the capacity sensor design. And then into the measurement side. So if I have such a capacitive sensor, so this is some sensor for some applications for biomedical, and I have the capacitance Cx. Okay, and I have parasitic capacitance Cp1, Cp2. So how to measure the value of capacitance Cx? The big question, right? So if I can measure the Cx value, I can measure the band. Okay, so what are the conventional ways and what are the challenges in the conventional methods, and how overcome that method challenges to accurately measure the Cx? Okay, yeah. So the most conventional method in a capacitive sensor or capacitance of a capacitive sensor is like having a block like this that need to change or convert the capacitance value to equivalent voltage or current, and we need to accurately convert this analog value to corresponding digital conversion or digital converted values, right? So basically it will have 3 stages. That is, I will connect a capacitor to a capacitance current converter. So the capacitance value will be converted to corresponding voltage or current value, which is proportional to X. Okay. And since it's a sensor, the value of the capacitance will be in picofarad, right? 100 picofarad. So the voltage will be in range of milli or micro range, millivolts or micro ampere range. So require some amplification so that it reaches to level which we can easily sample and convert to digital value, right? So I'll get some amplified voltage and will give to some analog to digital converter for digital output, right? A conventional method we use. So for capacitor voltage or current converter, we have pretty much many circuits which directly converts capacitance value to some voltage or current. So a bridge circuit. So you would have see bridge circuits like Maxwell or sharing. So this bridge is known as a sharing bridge. Okay, so whenever bridge is balanced, we can easily measure capacitance Cx in terms of C3 and R3. Okay, so this is a bridge. So here in this bridge, we will apply a voltage across this, and there will be a corresponding V voltage across the nodes here A and B, and this voltage will be proportional or a function of the Cx. So which means I'm converting the value of Cx in terms of voltage, right? So VAB will be something like 10 into Cx. Okay, so I can easily convert the value of Cx into voltage here. So this is a bridge type of capacitance to voltage converter. Okay, some other method include based amplifier. So here in a inverting amplifier, we'll just simply connect the Cx at its input. So what happens? I have j omega c as its input, and if I apply a signal here, I will get V0 to R the impedance, that is j omega cx into the Vi. So what happens again? If you see, V0 will be Cx. So I'll get signal here, some sinusoid whose amplitude will be proportional to Cx. So again, this is again a capacitance to voltage conversion. There are methods like switched capacitive network, where the capacitance is directly converted to the impulse of current. So this will be like an impulse train. Okay, and amplitude of this impulse will be proportional to Cx. So this is equal to the capacitance Cx. Okay, so if I have some other feedback network, I can easily find the capacitance Cx by balancing this capacitance and Ix, which is proportional to Cx, some other current, say some Is. If I compare this, we'll get the capacitance Cx very accurately. So these are some methods used for capacitance to current or voltage conversion. So once we get so once we get this voltage value, we will just convert to a readable range of voltage using an amplifier, right? So that is the voltage. So usually instrumentation or this measurement circuits, we use instrumentation amplifier at this stage. So it amplifies potential signal available here corresponding range which we require to convert to digital. So the most of the amplifier circuit will involve such INAs. And at the third stage, we have analog to digital converters. So we have type of analog to digital converters like flash type ADC, sampling and encoding, the conventional way of the conversion of analog to digital data, or SAR or dual loop conversion. So in most of the conventional methods, we use a sampling or encoding type method, so that the capacitance change directly convert to digital data by sampling rate. Okay, so for signal which has high frequency, we can use this data. But for more accurate results, we usually use for capacitance measurement, we usually use a dual slope conversion, where the voltage due to the capacitance will be integrated for time N1 Tc. So this will be like proportional to the capacitance Cx. And later we'll deintegrate the same voltage by some reference capacitance Cs. And we'll measure what is the time required so that the voltage reaches. Okay, so what happens is Cx will be equal to Cs into this N2 by N1. So we can easily measure the capacitance Cx in terms of the time required for discharge. So this is the method which is used for high accurate measurement of these capacitances. But the problem with such a digital conversion with the dual method is that the time required for conversion will be large. So for measurement, we cannot opt such type of conversion, right? So this is the conventional way of CX or converting of CX into digital data. Okay, so this is a conventional way. But when we come to a practical application, like in biomedical application or any application, though we know the capacity sensor is a variable capacitor, ideally, in non-ideal case, it's not like that. In non-ideal or in practical case, the capacitor, the sensor is not a single capacitor Cx, it has some non-ideal elements. So one element is the resistance Rp. So this is the leakage resistance. So if I have two metallic plates, okay, even though it's a single capacitor, there will be a leakage current flowing between the two plates. It depends upon, totally depend upon the permittivity or the type of conductivity of the material or dielectric element between the two plates. Right? So the capacitance Cx is non-ideal case. We should model it as a capacitance kept in parallel with Rp. So in usual case, the Rp will be in range of mega ohms or hundreds of mega ohms for a normal capacitor. But for a sensing capacitor or a capacitor in applications where the dielectric element is liquid or a flexible type of materials or at different temperatures, the leakage resistance used to go well below hundreds of kilo. Okay, even in applications like, especially like in moisture sensing, like the application that we discussed. Yeah, so in application which here for sweat or moisture patches or skin hydration, in all this application, the resistance may even go down to near to 50 kilo ohm or 10 kilo ohms range. So what happens? The sensor is not a single capacitor. This effect of this resistance will come into the output of the measurement circuit, right? As shown here. So if this is a capacitive sensor Cx, and if I use a conventional capacitance measurement, the digital data will be a function of Cx as well as Rp. And moreover, if the measurement circuit is we are using a conventional measurement circuit, the output also depends on the parasitic capacitance CP1 and CP2. So what is this capacitance? This is due to the shielded cable capacitance or even the stray capacitance available over the PCB. Okay, maybe the PCB of the measurement circuit itself. So this all may affect the digital data, output digital data. So we won't get a value which is directly proportional to Cx. So how to overcome these challenges, okay, in measurement? So we'll see that. So for that, we have a method known as phase sensitive detection. Again, it's a conventional method, but it's very effective in measuring accurately this capacitance independent of the leakage resistance, right? Yeah, so there are two methods in which we can measure. So one is a multiplier type PSD. So this is that multiplier type PSD. So here we have the sensor here, CX and RP. This forms the sensor. Okay, so this is kept at the input of this amplifier. So if you see here, this is an amplifier, right? This is an inverting configuration amplifier. And at the input node, I have an impedance of CX parallel RP. And I have an RF resistor kept in the feedback. Okay, when I apply a voltage here, VI, a sinusoidal input, what happens? There will be a flow of current like a current IX and there will be a flow of current IP. Okay, and this added value IX plus IP will flow through the resistance RF, right? So let me just clear this. Yeah, so it will be something like this. Okay, and what is the value of IX and our IP? IX is like, so this is a virtual ground, right? Volt. So what is this current IX? IX will be the voltage across this CX, that is VI, which is applied here, a sinusoid A sin omega t, by the impedance of CX, that is 1 by j omega CX. And similarly, the current through RP will be IP, which is VI by RP. Okay, and this current will flow through the resistance, which is given as IF, that is this is equal to IX plus IP. Okay, so what happens? This current IF into RF will be the voltage V0 1, right? So IF into RF minus of IF into RF will be the voltage. So we can write the voltage as like this. So I have a voltage due to the resistance RP and I have a voltage due to the capacitance CX. Okay, so we'll have two components, and if we carefully see the two components, so let me, yeah. So when we check here, see, this component is a real term and this has a j omega term, right? So this is an imaginary term. So what happens is like this will be an in-phase component, like this will be a signal which is in phase with the sinusoid, and this is like j omega, it's a imaginary term, right? So it will be in quadrature, so it will be sine signal, right? So I will have the summation of both sine and cosine. Cosine will be proportional to Cx. So how to measure the signal which is proportional to Cx? So what we will do? We will extract the value or the amplitude of this cosine or quadrature phase so that I can accurately measure the value of Cx, right? So how to do that? So this is a component which is proportional to sine omega t, and this is a component which is proportional to cos omega t. So the simple method is like simply multiply this with cos, right? We'll multiply with this cos and we'll just give to a low pass filter. So sine omega into cos omega t, if I integrate, it will be integrated to 0. And if I multiply cos into cos, I can integrate that to a constant value which is proportional to its amplitude, right? So that is a basic principle which is used here. So I have this in-phase and quadrature phase component V01 here, and this in-phase component A sin omega t is given to 90-degree phase shifter, so that I will get a cos component, right? So A cos omega t, and I'll give to a multiplier here, and the output of this multiplier will be Vm. Vm will be equal to V01 into this A cos omega t, right? So as shown here. So when I bring this cos omega t inside, so this into this will be sine into cos, it will be proportional to sine 2 omega t, right? And when I multiply this cos omega t and cos omega t, it will be like cos square omega t. So it will be proportional to that cos 2 omega t minus 1, right? So we'll have effectively this Vm will have two components, that is a component twice the frequency and a which is proportional to DC, right, with 0 frequency. So how to measure the Cx? We just need to give through a low pass, right? So our objective is to measure the value of Cx or the component proportional to Cx. What we'll do, we will integrate it, or in effect we'll give to a low pass filter, and the output of the low pass filter will be the DC component Cx, right? So effectively, the output, if you see, it is made independent of RP, right? So the component of RP is actually eliminated in the output. So the multiplier type PSD helps to over effect of Cx, right? The output will be directly proportional to Cx independent of the value of RP. So even if the changes, or if the low value leakage or the leakage resistance changes due to the temperature or due to the presence of some conductive element between the metallic plates, all these are actually created, right? And only the change in the capacitance due we can be measured using this multiplier type PSD. So it's a direct method and a very effective method in value of RP, right? So this is the multiplier type PSD. But the main challenge of using such multiplier type PSD is that use of multipliers. Okay, so though we write Vm equal to V01 into the quadrature component, when we implement such a multiplier, the output may not be linear. There will be a lot of non-linear components which affect the output. So in regard of this sensing, those non-linearity will create huge error in measurement. Okay, and also there will be a lot of complexity while implementing these multipliers. So how to overcome? So even though this is very effective method, how to overcome these challenges due to the multiplier? So the best method to do that is like using the second way or method, that is switching type PSD, where we'll replace the multiplier using a switch. So you could see here. So this is a SPDT switch, right? And this switch is controlled by it's VOC, voltage output of this comparator. So whenever the comparator output is 1, this switch will be connected to this position 1. So whatever signal V01 will come here, and whenever the voltage at VOC is 0, the switch will be connected to the position 0. So whatever the signal here will come. So there is an inverter here, so it will be minus V01 will be coming to Vs. So we can easily switch as a pathway to select whether I need to integrate V01 or minus V01. So we'll see how this can help in measuring Cx independent of RP, right? So if you see the circuit, the other part of the circuit are same. So we have again the inverting configuration of amplifier. At the input we have the sensor and RF feedback resistor. I have phase shifter, and the output of this amplifier is connected to one end of this SPDT switch, that is pin 1 directly, and to pin 0 by inverting this. So I will have a minus V01 signal here, right? So what happens? So similar to the previous circuit, the current through this capacitance and resistance will be same. Ix, and I will have a current Ix and Ip, which will flow through the resistance RF. So it will be like equal to Ix plus Ip. And because of that, there will be a voltage, similar voltage in phase and quadrature component voltage at V01. Correct? So I'll call this in phase component RP and the quadrature component equal to VCX, denoting that in phase is to or a function of RP and VCX is a function of CX, right? So if I draw this signal, okay, so I have our input signal Vi, which is a sinusoid here, okay. So what is VRP? VRP is the voltage corresponding to RP, right? So it is actually minus RF by RP Vi. So I will have the same in phase sinusoid signal as shown here, but it will be inverted due to this inverting configuration. And what about CX? It will be a 90-degree. So I'll have an inverted cosine wave as shown here. So these are this summation of voltage will be V01, right? Which is available here. Okay. So how I can use these two signals and simply measure Cx, that we'll see. So I have the same shown here. So I have Vi, I have VRP and VCX. Okay, the summation of these two signals is V01 as shown in the previous slide. Okay, now if you see here, I have a cosine signal at the output of this shifter, phase shifter. So I have a cosine signal. So what will be, so this is a comparator. Okay, so output of comparator will be a square wave, right? So it will be high whenever the cosine is high, and it will be low cosine is low, right? So this is corresponding to 1 and this corresponding to 0. So whenever the signal is 1, these connected to 1, and if it is connected to 0, right? So we'll see it here. So this is VOC. Time when VOC is 1, okay, when VOC is 1, what happens? The switch is connected to position 1 here. So what is V01? The same signal will be arrived at Vs. Okay, so at Vs, if you so the same signal V01, which corresponding to VCX, the same signal will be at the output. So that is shown here. So this Vs, the voltage corresponding to VRP will be maintained, and the voltage corresponding to VCX will be also maintained. Okay, now when the VOC is corresponding to the voltage 0, happens. Another color. Yeah. So when this 0, what happens? This switch will be connected to this point, right? So what is here? Here we have minus V01. So minus V01 will be available at Vs. So if you care here, right? So at Vs, VRP. So VRP was like, right? So this signal inverted at Vs. So we'll get an inverted signal like this. So this half and this half will be inverted when VOC is 0. And the voltage corresponding to VCX is this one, right? So this will be again inverted like this. And similarly now, so this signal is inverted. Now again, when the voltage is VOC is 1. So when this is 1, again the same signal will be available here, right? Same signal which was there at VR replicated, and the same signal which was for VCX, it will be replicated at the Vs. So if you carefully see the signal at Vs, right? Sum of VRP and VCX shown here. And if you see here, the VCX is like a full wave rectified signal, right? It's a rectified signal. That is, signal corresponding to CX will be rectified. And if you see here, VRP, it is like the half of each period is actually inverted. So you'll get a signal which is somewhat similar like this. So if we give this signal integrator, okay, if I apply this signal to an integrator, what happens? The output will be proportional to integrated value, right? Output will be proportional to the area under the curve, right? So what happens if I integrate this signal? So if I take a single period, if I take this period, this signal plus this area integrated to, the value will be integrated to 0, or we can say average is equal to 0, right? Average is equal to 0. So that is the case for period. Now what happens to, so I guess yeah, some network issue. So I guess my screen is visible.
Yes, sir, it's visible.
It's visible, right? So where did I miss? I didn't know. Yeah, okay. So yeah, so let me start with VS. So when we say VS, it will be like a rectified signal which is proportional to Cx, and a somewhat signal like this with average 0 for RP. So the output of low pass filter will be equal to Cx and independent of RP. So that is the output of a switching type PSD, right? And so we are implementing the same circuit which saw here, uh, instead of multiplier type, which is a switching type, but we are attaining the same. So I guess there is some issue with the network. Yeah. Yeah, my screen is visible and I'm audible, right?
Yes, sir.
Yeah. So let me. So that's what about the PSD. So I guess all of you got a overall picture of designing the capacitive sensor and designing an effective circuit which can all these non-idealities, right? So with this, let me conclude today's talk. Yeah. So let me conclude this. Already there is some issue with my network. I'm good that. Yeah. Yeah. Okay. So yeah. So that's what about the making the output independent of the RP, right? So if I have a, even though if the resistance goes well below a value of 10K or 100K, we can easily measure the output independent of RP, right? Now, other challenge that we discussed was that the effect of parasitic capacitance. Okay, so apart from this leakage resistance RP, the other parasitic is like the parasitic capacitance CP1 and CP2, which is the non-ideality. So in a normal sampling or normal conventional way of measuring the capacitance, the output will be heavily dependent upon the capacitance value CP1 and CP2. So what is the issue with this CP1 and CP2 is that whenever there is a change in this capacitance CP1 and CP2, it will affect the output. Apart from that, the capacitance value of CP1 and CP2 will be comparable with the capacitance value of the sensor. So usually the sensor value will be near to 100 picofarad. This parasitic capacitance can go till 50 picofarad due to the long lengthy coaxial cable, right? So what happens? There will be large offset in the measured output. So it will create a huge error in measurement. Now we'll see what is the effect of this capacitance at the output. So if we see here, if I apply a voltage Vi, so what happens? There is a voltage Vi here. Okay. So since there is a voltage Vi, there will be a corresponding current here, right? So I'll call this IP1, and this is virtual ground, 0 volt, right? So what happens? There is a current here, Ix. There is a current IP. Same current Ix and IP which we discussed earlier. Okay. So does the CP1 affect Ix and IP? No. Why? Because the current, definitely there will be more current will be pulled from this source, But the thing is like this IP1 will flow into the ground to CP1 while it won't affect the IX and IP. Right. So there is no effect of CP1 in this circuit. Okay, in this proposed circuit. And now corresponding to the current due to CP2. So definitely there will be a current flow through the CP2, right? So if there is a current flow here, this IZ won't be equal to IX and IP. Why? Because a fraction of this current will be flowing through CP2. But if we carefully see here, the voltage at this node is zero because of this ground, virtual ground. And this node voltage is also ground. So what happens? The current through this, say I will call it as IP2, the current IP2 will also 0 ampere. So what happens? Z is always be equal to Ix and IP. So ineffectively, the effect of CPU and CPU2 is actually nullified by or inherently nullified or eliminated by this design, right? So the output is V0 1 will be proportional to Ix and IP, and if I use the same switching type PST, V0 will be proportional to Cx. So the entire circuit make the output independent of both as well as CPU and CPU2. So we'll get a very accurate values of Cx, right? So with this, let me today's talk. So we discussed about a capacity sensor. So capacity sensor are widely used in most of the biomedical application, especially in wearable type of sensors. And we saw what all things we need to take care. Definitely, we need to the sensor such a way that the Cx has high sensitivity, right? The sensitivity directly depends upon the area, the distance between the plate and the permittivity. Okay, so that and all is like design aspect related to what sort of sensitivity you require. But apart from that, what all things we need to take care about the accuracy of result, accuracy of sensing measurement. So for that, we need to take care about the parasitic effects or the interference effects. So how to overcome that? We can use various guard rings or shielded cables, which we discussed, right? So this effectively helps to improve the accuracy when we see the sensor itself. But when we go for real-time application, apart from this capacitance Cx, we saw there are some other non-idealities known as the leakage resistance, the parasitic capacitance effect, right? So how to remove that? So we discussed some of the effect methods to overcome that. That is PST-based techniques which we can use to effectively remove the effect of RP and CP1 and CP2, right? That was the whole idea. So with this, I guess, with this lecture, I guess you can easily sensor and accurately use the sensor to measure the required measurement in any applications, right? Yeah, so that's all. Let me stop here. Thank you. So any questions?
Thanks, sir, for the informative and insightful session. We truly appreciate the knowledge and expertise you shared with us today. Now, I would like to invite the participants to share their feedback, comments, or questions regarding today's session.
Yeah, thank you. So any questions, like any?
As there are no feedback questions, we shall
Uh-huh.
now send a token of gratitude to our esteemed resource person in appreciation of his valuable time and insightful session.
Thank you.
Once again, on behalf of the Department of Electronics and Communication Engineering, the Institute of Management and Technology, I extend our heartfelt gratitude to Dr. Narayanan P P for taking the time to be with us and for sharing his expertise. We wish you all the very best in your future endeavors. Thank you, sir.
Sure. Thank you so much. So I think I'll stop sharing, leave this session. Yeah, thank you all. Yeah, thank you so much. Yeah. Thank you, right? Thank you.
We shall now move on to our next session. It gives me immense pleasure to introduce our next esteemed resource person, Dr. D. Menaka, Associate Professor in the Department of Electronics and Instrumentation Engineering at Nurul Islam Center for Higher Education, Kumarakhoil. She is an accomplished academician and researcher with over decades of teaching experience and a decade of research experience. She earned her PhD in Electronics and Instrumentation Engineering from NICHE with her doctoral research focus on innovative methods for land cover classification using multispectral satellite images. She has made significant contributions to the fields of digital image processing, artificial intelligence, advanced computing, and industrial automation through her research publications, conference presentations, and academic leadership. She also guided several research scholars towards their doctoral degrees and continues to mentor aspiring researchers. Today, she will be sharing her expertise through a session on smart grids, AI for energy optimization, and sustainable automation, a topic that is highly relevant in the context of modern energy systems and sustainable technological development. We are honored to have her with us and eagerly look forward to gaining valuable insights from her session. Ma'am, the virtual floor is all yours.
Yes, ma'am, your presentation is ready. It's visible, ma'am.
Okay. I'll join by 5 minutes. Okay.
Okay, ma'am. No
Okay.
problem.
Camera വേണോ? Hello?
Yes, ma'am.
മാഡം സ്റ്റാർട്ട് ചെയ്തോളൂ. ക്യാമറ വേണമെന്നില്ല.
Sarpan-oriented architecture. It's called as a model.
സ്ലൈഡ് ഷെയർ സ്റ്റാർട്ട് ചെയ്തോളൂ മാഡം.
So good evening, all. Dear participants, today we are going to have a session on smart AI for energy optimization and sustainable automation. So here I am myself, Dr. D. Menaka, Associate Professor, Department of Electronics and Instrumentation Engineering, Noor Islam Center for Education, and very okay. So let's start. So organizers, start. Whether my voice is audible?
Yes, ma'am. Audible, ma'am.
Okay.
Audible.
Okay. So today's session is on grids. So as we all know that nowadays electrical utilization is going increasing by day to day increase in our demand. So initially conventional grids are converted into microgrids, and then it is nowadays we say as smart grids. That is, it is utilized with the AI and IoT and edge computing, like that, with so many advanced technologies. So the grids are converted into smart grids nowadays. Okay, so now so that we call it as sustainable automation. So that is our living style all changed because of the smart grids, and we go to that is we are adapting the value on present as well as future. Therefore, this are called as it's a valuable one for sustainable automation. Okay. So on by this session, we will have the outcomes like we'll understand the what is meant by smart grid, what is the architecture of smart grids, then how it is explored using AI techniques, then how the energy systems is optimized, and there are so many automation applications, and what are the case studies. There are several case studies relevant to the smart grid. Okay, these are the outcomes, and so start with the challenges of global. That is, first one is rising demand. So based urbanization, industrial development, and electricity consumption of population. So and also increased in electric EVs, that is electric vehicles. Then data information centers, devices. So we require more energies. Okay, so it's a challenge to meet this demand efficiently and sustainably. Okay, so next one is climate change and decarbonization. So this banning for fossil fuels, it increases this greenhouse, it releases greenhouse gases, which is causing global warming. Then so countries are adopted to reduce its carbon emissions by adopting renewable energy resources. So the to achieve a cleaner and green environment. So this is also one of the challenge. Then renewable energy integration challenges. That is the nowadays the renewable energy means in the sense that is the solar, wind energy, water resources. They should be clean, but it depends on the climatic also. So their output power will be varying throughout the day based on the environmental. So that is also a big challenge nowadays. That is, we have renewable energy based on the climatic change. We cannot get renewable energy resources. So it is one of the challenge. Then reliability and resilience. So increasing demand make there is continuous fall. Okay, so the electricity falls, then big natural disasters. Also, there is a low in smart grids. So that is also one of the challenges. So again, there is a need for intelligent automation to adopt smart grids. So grids in the itself, it is adopted with machine learning, IoT, so on. So intelligent automation should improve when we are integrate, that is AI techniques should improve its efficiency. It reduces its cost. So it should support the integration of renewable resources. So everything. So these are all some of the global challenges. Okay. So next one is we'll go what study the introduction about power grid. So Thomas Edison. So this is the conventional power grid. Okay, so the conventional power grid is found by Thomas Edison, who is the father of DC direct current distribution. Then we say Nikola Tesla. He is the father of alternating current or AC distribution. Okay, so these are all the founders of grids actually. Okay, so Tesla's inventions for long distance AC distribution were commercialized in competition against Thomas Edison's short distance DC distribution system. So when comparing to DC distribution, so AC distribution will be utilized for long distance. Okay, so automatically this AC distribution one thing. Okay, excuse me. Hello. So features of changing electric power grid networks. This is the normal conventional grid system. So here it is a one-way communication. The main disadvantage here is the main disadvantage in conventional grid system is it is a one-way system. Okay, so we cannot get any feedbacks or any results from the customers to the utility centers. Actually, utility centers means the distribution centers, that is main distribution stations. All are utility centers. So we'll does not receive any feedback from the customers to the distribution. That is the only drawback of conventional grid system, and also it is not integrated with the systems. Okay, so that is the main drawback. It consists of three steps. That is energy generation, transmission, and distribution. This all okay. So these are the basics. That is how the smart grid emerges from the conventional grid system. Okay, so we know that because of the demand, only this smart grid comes into exist. And how this is the picture which shows the comparison below smart grid and after smart grid. Okay, so we can see in this picture that it is a one-way power flow, and it has only simple interactions between the customer side and the utility, that is distribution centers. Okay, so in this after the emerging of smart grid, we can see that the two-way power flow, and it has the interactions between multi-stakeholders. That is the center, then commercial centers, domestic centers, then apartments, smart houses, that is power plants. Then it may have a control center. Through the control center, the data can be transferred to the utility as well as distribution via the power stations. So this picture explains the difference between before smart grid and after smart grid. Okay. So now we come into introduction into smart grids. Actually, smart grid is an electricity network uses digital communication. So this uses communication, sensors, automation, and artificial intelligence to monitor, control, and optimize the generation, transmission, and distribution systems of electrical energy. So we know that the conventional grid system has generation, transmission, and distribution stages. And these 3 stages can be integrated with AI and digital communication sensors. Okay, digital communication sensors and automation to which is mean by. Okay, so the basic thing is, unlike traditional power grids, which allow only one way of power flow, this enables two-way flow of both electricity and data. Okay, that is how much demand the customer needs, how much they have utilized, what is the future needs of the customer, and what is the efficiency they need. So everything, every information or data can be collected from the customers to the utility center. Okay, so this is the thing between the conventional grids and smart grids. Okay. So this is the pictorial representation which explains the smart grid, which transforms the electric grid into digitalized electricity network. Okay, so it involves smart sensors, smart meters, then communication network, automated control systems, AI, then machine learning algorithms. Everything is adopted together, which is meant by smart grids. So this figure shows the 3 stages, and that is generation, transmission, distribution. Okay, so generation from the utility centers, wind, renewable energy sources, that is how the electricity is generated from the wind farms or solar power plants or hydraulic electric power plant or nuclear power plant, everything. Okay, all the power plants are comes into generation. Then it is transmitted through the transmission centers or substations, then be distributed to the customers. Okay, that is either it can be initial or commercial purpose. Okay. So these are the benefits of smart grids. So as I already said, it is a digitalized network. And next one is, it is a two-way power transmission, transmission as well as information. Then we can always control and monitoring. That is real-time system. Then it is a user-friendly or eco. This consumer participation is there. Integration of distributed energy resources. D we will say yes. D here we will see it later also. So one by one we'll study. So digital electricity network. Digital electricity network. So that is it is we know that the smart grid which transforms their conventional electric grid into a digitalized network. So it has smart sensors, smart meters, then this communication networks, and automated control systems and other algorithms. So we know that it works means, so there is these sensors, meters or smart sensors, it collects data like age, current, frequency, and power, etc. Okay, these data can be transmitted for analysis as well as for making the decision. Okay, so that is nothing but digital electricity network. Okay, next one is two-way power and information flow. So this one is the traditional grid from the power plant. It is transmitted to the consumer only one way. And next one is when comparing with the smart grid, we say yes, it is a two-way power information. Okay, so from the power plant to the grid system, then consumers again, it is fed back to the power. It has the utility center. Through the utility center, it is all the data transmitted again from the consumer to the distribution. Okay. So this is the structural or architecture of a smart grid, which shows the two-way structure. So here, see. these are the power plants or solar or wind farms. So here it is transmitted and it is given to the industrial centers. Okay, so this is e-vehicles. So e-vehicle is increased now. So it is also given. So and this dark blue is from the distribution. Sorry, from the transmitted and it is distributed to the customers. Again, light blue color shows the bidirectional way. Okay, that is the it is given to the control center. Okay, data is transferred or information is transferred to the control center. Okay. Then real-time monitoring system. So real-time monitoring system in the sense this smart grid will continuously monitor the conditions. Okay, so it some advanced device. It is mainly this phase measurement units. So other along with smart, it has PMUs, that is phase measurement units. Then intelligent electronic device. Okay, there is IEDs. Then SCADA systems. Okay, so this the functions of the real-time monitoring and control section is it will monitor the load. Okay, it tracks the electricity demand of the customers instantly and continuously. Then any fault can be detected quickly. Transmission grids, and then the voltage levels. The stable voltage levels can be maintained, or a constant voltage can be maintained. Then it ensures the stability, that is frequency stabilization also. Okay, so these are the functions of the real-time monitoring and control unit in the smart grid system. Okay, next one is customer participation. So customer participation means in the comparing with the conventional grid, this the consumers is think of the user. Okay, the users, they became active participants. There is then this smart grid comes into exist. Okay, so as it has smart meters, so it will provide continuous or real time informations. Okay, so it optimizes the energy, can be optimized by this smart grids. And okay, the demand, based on the demand, we can have the electricity. Their response can also be notified. Okay, so this is consumer participation is there. Then integration of energy resources. So distributed energy resources in the sense they are a small scale power sources located near the consumers. Okay, so for example, these are the DERs. That is, DERs means simple water distribution centers which can provide electricity, generate electricity. Okay, so solar voltaic systems, that is adopted in solar power plants, then wind turbines, then battery energy storage systems, electric e-vehicles, fuel cells, then microgrids. These are all considered as distributed energy resources or small scale generation systems. Okay, or small scale power resources. So evaluation of power grids. So we'll have the step-by-step advancements in the power grids. So first it is the conventional grid, then automated grid, then digital grid, then smart grid, then AI enabled autonomous grid. So conventional grid, it is a one-way system. Then as the system is in the conventional grid, there is the difficulty to identify fault detection, and the system is also less efficient. Okay, efficiency is also very less. And now next to that as the technology is advanced, then automated grid system emerged. Okay, so in the automated grid system, control system like SCADA means supervisory control and data acquisition system. So the SCADA system is integrated with the in the automated grid system. Okay, so it is SCADA is actually utilized for remote monitoring purpose. So remote monitoring and for controlling the grid operations. Okay, can improve automatically when comparing conventional grid. It improves the fault detection easily, and it also increases the efficiency of the system. Okay, so therefore this consumer utilization is increased in the automated grid system. So the next stage of automated grid system is digital grid. So it incorporated digital communication networks. Okay, like advanced sensors and some data management systems. Okay, so this the real-time information can be transferred. First, it is collected, transmitted, analyzed, and can be monitored and in the digital grid system. Okay, so this digital grid system is user friendly, and it is used for making decision making easily. Okay, that is it. It is for the bidirectional operation. Okay, that is digital grid system. Then comes the smart grid system. Okay, so the smart grid we know the digital. It's actually the digital grid system only, and here it is adopted with this everything that is digitalized networks, digitalized communication networks, smart sensors, then all the smart meters are incorporated in the smart grid systems. Next one is the AI enabled, so incorporating artificial intelligence, machine learning, then twin technologies. So nowadays digital twin technologies is adopted in the autonomous system. That is the present stage of the technology. Okay, so it is efficient in optimization of energy systems. Optimization in the sense the value, the demand is automatically changed according to the prediction. Okay, according to the prediction of the future demand of consumers. Okay, so that is the advancements in the power grids. Okay, so this is the architecture of smart grid. So it has smart grid architecture, advanced electrical network, and it involves generation, transmission, distribution, then consumers, and communication infrastructure, and mainly control center. Okay, so this is the structure of the smart grid architecture. This here it shows the transmission, distribution, and it has mainly the controls. So all the lines, it shows the bidirectional distribution centers. Okay, so this is the smart grid technology, and the structure I already explained. And you can see that it is the architecture of the smart grid systems. So in the architecture, we can see the main components of smart grids like smart meters, then PMUs, then SCADA systems, IoT device, advanced communication network, energy management systems. Okay, so what is meters? Means it is nothing but it is a digital devices which can use to make electricity consumption. Okay, in real time. So the smart meters are fixed in the consumer's location, and they are used to measure the electricity consumption every time. Okay, instantly it can be reduced, and it also enables this two-way communication between consumers and utilities. So then the sensors and phasor measurement units, so PMUs. So PMUs also, it is also used for continuously monitoring grid parameters. The grid parameters like this voltage. What is how much voltage is taken, and how much current is taken, and what is the frequency of the unit, then a phase angle, everything. These are the parameters. This can be measured by PM. Okay, so it provides accurate measurement. Okay, it provides accurate measurement, and it helps the operators in the utility systems to detect the faults, and it prevent large damages. Okay, so like this conventional or traditional systems. Okay, then it has SCADA systems. SCADA is nothing but supervisory data control and data acquisition systems. So it collects the data from the substations or stations, and it transmits to the control unit. Okay, it transmits to the center or control unit. So you can see the control unit here. So this is the control unit. So here the SCADA system. Here we have the SCADA center. Okay, so it collects the data from stations. So the diagram is shown here. Okay. Then the engineers or engineers will use the SCADA systems to monitor the grid conditions, and it is used for detecting faults, managing power system operations very efficiently. Okay, so then it has IoT devices. Okay, so devices, it can connect via the cloud or internet. Okay, so these devices can be used to conduct exchange data and enable real-time monitoring systems. Okay, so then this has what advanced communication infrastructure. Okay, advanced communication infrastructure. It means it involves communication networks. Okay, communication networks, which is used for two-way communication, two-way flow of information. Okay, then it has energy management systems. Okay, so energy management systems. So energy management system is shortened as EMS. EMS nothing but it is a software. Okay, it is a software unit which can analyze the data from the smart grid, and it helps optimizing energy generation, transmission and distribution, and then consumption. Okay, okay, so it helps optimizing the energy generation, transmission, distribution, and consumption. Okay, so this EMS system, this EMS or this software only, it is used for predicting load forecasting, then weather forecasting, then integration of renewable energy, demand response ability. Okay, so this EMS enables increase in efficiency, and it maintain a good reliability grid operations. Okay. So this is the smart meter building system, and this is the structure phase measurement unit. Okay, PM is it can measure this parameter. Okay, parameters like voltage or frequency in the utility as well as the consumer locations. So the installation of PMU, it needs three-phase AC signals and the phase rotation, phase angle, its magnitude, and then a phase. Okay, phase, and it needs a GPS and other and some networks also. Okay, so installation need of a PMU. Okay. So here is at the input side, there's the three-phase signals, potential transformer or current transformer inputs. Then we'll get the digital or phasor data. Okay, and there's a readable device, a display unit. The parameter measurement can be displayed in this reading device. Okay. it is also synchronized with the GPS system, and you can also note the value in the using some GPS devices also. Okay. So this is the SCADA unit. That is supervisory data control and data acquisition system. Okay, so it collects the data from the substations. So it's a graphical representation of this system, and it collects data from the substations like and otherwise, and also sensors. Okay, sensors, and that data is transmitted to the control unit and operators. This is the control unit. Okay, this is a control unit, and the operator, it uses the SCADA system to monitor the grid conditions. Okay, it remotely control and monitor the remote grid conditions, and the fault can be identified easily. Okay, SCADA systems. Okay. Then the IoT devices. So this is the smart device. So you can see data from the distribution or the distribution center. Distribution means consumer section to the using our mobiles or mobile app. Okay, so the IoT is nowadays used in smart and everywhere it's adopted, and smart grids. Smart grids actually uses IoT for continuous monitoring data from the sensors. Okay, so it exchange the data during the real time monitoring systems. Okay, so that is this is the representation of the IoT.
Or the online
Excuse me. Hello, excuse me. Okay, so whether I'm audible? Hello.
Yes, ma'am.
Okay. Okay, so I'll continue. So this IoT devices, then it's the graphical representation of the IoT, and then communication networks. So communication networks, so it's a communication infrastructure which has this WAN and HAN networks. That is, so this communication networks which uses this Wi-Fi or WiMAX, then 3G wireless networks, 4G, 5G, like this communication networks. Okay, so without the communication, the IoT is not integrated. Okay, so for that, all the things are integrated in the systems. Okay, this is the complete setup which shows the smart grid communication and monitoring systems. Okay, so you see from the supplier, there is the windmill or solar or anything, and in the control unit we have a SCADA system. Okay, control unit has a SCADA system, and this system which consists of a set of and which continuously monitor and manage the power systems. Okay, so this SCADA system which collect information from the utility center and analyzes the based on the operating conditions, which is used for detecting any fault diagnosis, and it again sends the commands necessary to the control unit. Okay, here it is in a electricity supplier. So the supplier is power plants. Okay, power plants which generates electricity. This is the generation unit. Okay, generation unit, and this electrical energy is to the consumers through a grid system or power network. Okay, so power network is the grid system. This transmission and distribution lines. Okay, so here electricity supply as the generation, then comes transmission as well as distribution, then the consumption. Okay, so this electricity flows from the supplier to the residential consumers connected to the grid. Okay, so this SCADA is interconnected via the residential unit through the Wi-Fi system. There are communication or communication networks like this Wi-Fi or WiMAX or 3G, 4G networks. Okay, so this is the bridge between the smart sensors, substation, and the control unit. So which enables the exchange of information for real-time monitoring. Okay, so then these are all the residential or consumer units. Okay, then we have the substations. So here is the substation 1 and substation 2, which represents the utility operators. Okay, they are the operators present in the substations, or the owner, nothing but the operator. Okay, they get the information from the control via the so for operating the control unit we need the communication network, so everything is integrated. Okay, so from the control you get the data to be informed to the substation owner, that is operator. Okay, utility operator. So you can monitoring the unit. Okay, they will be at the remote location. Okay, they will be operating at the control substations using their mobiles. So communication technologies are the communication. There are different networks available. There is PLC communication. So PLC nothing but power line communication. Okay, PLC is power line communication. So first you will see one by one. There is PLC. Then another technology is fiber optics. Then wireless is available. Then 5G and edge computing. Then industrial IoT. Okay, IIoT. So these are all the communication technologies adopted in energy systems. So for PLC communication, so PLC here represents communication. Okay, so power line communication means it is a technology that uses the electrical power line to transmit data along with the electrical power. Okay, so it uses electrical power, existing electrical power. Okay, it uses some existing electrical power lines to transmit data along with the present electrical power. Okay, so this PLC eliminates the need for separate communication cables, and there's once that signals are imposed into the electrical power signal, they are traveled through the same transmission or distribution line. So the smart meters which adopts this PLC, which is used for energy optimization. Okay, so PLC is the main component of the smart meters. Then comes the fiber optic communication. So this fiber optic communication, it is one of the communication media which transmits information as lights. Okay, light energy through optical fibers. Okay, so it is one of the fastest and also good reliable communication. Okay, communication technology used in smart grids. Okay, then the wireless networks. So here this is the structure of the wireless networks. So it has it has the technologies like Wi-Fi, then Zigbee, WiMAX, etc. So Bluetooth or cellular networks, and it is widely used in smart grids. Okay. Then here it is shown that there are 3 levels of meters. That is medium, then long range, then short range. Okay, for a medium range communication, so this Wi-Fi cables are used. Okay, for long range, it is WiMAX or Wi-Fi WiMAX as well as Wi-Fi are used. Then for Zigbee or Bluetooth is for short range link. Okay, so it is mainly adopted for this HAN or we'll say as so home area network. Okay, so home area network means which is a residential purpose, which has several connected with several smart devices, that is e-vehicles or solar systems, then smart appliances. Okay, smart appliances in the sense many electric devices. Okay, so this totally consists of home area network. So this smart grid communication network is operated for this home area communication networks. Okay. Then here we can see a distribution base station. Base station means the main station, and here it is distributed to the other stations like substations. Okay, substations are which this enables distribution automation. Okay, distribution automation means from the main station the energy can be distributed to DA systems or distribution automation systems. Okay, so which just represents the communication nodes between the distribution centers. Okay, So the base station is a main server, or it acts as a communication. Okay, so it collects data from different devices, different sensors, and it can be transmitted via distributed automation sensors. Okay, otherwise substations, distribution substations. Then 5G and edge computing. So 5G communication technology is which transfers smart by providing high speed. Okay, not high speed. It gives ultra high speed communication, and which is used to connect devices simultaneously. Okay, that is 5G communication technology. In traditional systems, the data is sent to a simple server for processing. Okay, but with the edge computing and this 5G as well as edge computing, the data processing occurs from a large data. Okay, the data processing is used from a source of large data, and they are big data. So it improves the efficiency, but it reduces the response. Okay, there is one disadvantage that is it gives reduced response time. Okay. So this structure has 3 layers. That is device layer, the transmission layer, and edge layer. So device layer is nothing but it is a basic layer where energy devices and sensors are located. Here we can see the grid system. The source means photovoltaic devices or any source where we get the power, and sensors also. So sensors are all located in the device layer. Okay. Next is the transmission layer. So here it carries the communication networks. Okay, so communication networks are present in the transmission layer. Then the edge layer. So edge layer serves that it processes data and it can make decisions. Okay, so it is the main. That is the device management layer. Okay. So the data collected from the sensor. So sensor is present in the layer. So all the data is collected from the sensors are transmitted through the transmission layer, and this has the PLC, that is the power line communication system, and wireless networks. Okay, wireless networks. So this utilizes electrical power lines to transfer data, and which optimizes very high speed. Okay. So mainly this transmission layer or the communication adopts OFDM modulation system. There is orthogonal frequency division multiplexing. Okay, so the modulation technique adopted here is orthogonal frequency division multiplexing. So it is used in actually in modern wireless communication systems. Okay, so it can adopt this 5G wireless techniques, and it is mainly used for digital broadcasting and so on. Okay, so and also it provides very high speed data, and so this FDM is adopted in modern communication modulation as a modulation technique. Okay, so that is used, and after the communication, the data is given transferred to the edge layer. Okay, so the edge server which decides how the computing resources should be allocated to achieve high efficiency. Okay. So instantly the fault detection or grid protection or the operator safety, everything can be processed immediately through this edge layer. Okay. Then industrial IoT platform. So that is IIoT platform. So IIoT means it connects the smart devices, then or sensors or actuators, any instrumentation or the industrial devices through IoT. Okay, through in. Okay, so it can connect smart devices like sensors or actuators or control devices or instrument devices or like transformers, everything. Okay, all industrial equipments can be connected via internet. Okay, that is IIoT. So IoT platform here, it collects data from thousands of sensors and use cloud computing. Okay, use cloud computing, then AI to generate insights for decision making. Okay, so here by using this industry, the failures of one can be analyzed and it also improve the overall performance. So here you can see structure of the IoT platform. Okay, so this is the simple example of IoT. So it connects industrial device, there are sensors, water meter, electricity meter, gas meter, heater, then high voltage device. Then this is AC. Okay, healing, then ventilation, and AC. Okay, that is type some device. Then everything are connected. All the devices are connected in the device layer. Then it is then the next layer, gateway layer. Here it is one of the key layer of the IIoT because it performs efficiently. Here, see these are the advantages here: device connectivity, data acquisition, edge compute, cloud access. Everything can be done in the gateway layer. Okay. Then IoT platform. IoT platform. Here all the sensor data, everything is integrated to the okay. All the data can be integrated via this communication path, the internet. Next is the energy management system. So that is EMF. Okay, and the mobile app is given. So it represents the application. Okay, application layer. So you have 4 layers: device layer, gateway layer, platform layer, then application layer. Okay, so in the application layer you have energy management system. So it is only control control everything. Okay, so it can only energy system can control the demand side equipment of the consumers, and it is viewed by using the mobile app. Okay. So finally, we can say that the industrial devices are the sensors. Industrial devices are then the intelligent are this networks. Then IoT platform works together to form IIoT. Okay. Then role of AI in energy systems. So these are different roles of AI in energy systems: data-driven decision, then automation, then prediction and forecasting, and optimization, self-healing capabilities. Okay, so data-driven decision making in the sense, so it this using the AI. How AI functioning in the energy systems are Okay, that is what we are seeing. So AI analyzes real-time and historical data or the previous data from the energy systems and to support the future decisions. Okay, so that is what data-driven decision making. So, for example, so this AI can analyze the demand of the consumers, then how the what is the market demand of the electricity in either in commercial as well as residential. Then how the system can be improved, performance or efficiency can be improved. Everything can be analyzed. Data-driven decision-making system that is done by AI. There is one of the role of AI in energy systems. Then the automation. Okay, so the automation in the sense all the sensors like it can this HVAC system or smart devices it can be automated. Okay, that enables that the so AI enables so automation. Then prediction and forecasting. So prediction and forecasting means some machine learning algorithms are there to predict the electricity demand, then renewable energy generation, everything. So any weather condition or there is a how the peak or the future electricity demand can be. Okay, that everything can be predicted by this AI incorporating AI. Okay, then optimization. So optimization is nothing but continuously monitoring or getting the operating conditions for energy systems. So that is done by the AI. And then self-healing capabilities. Self-healing capabilities in the sense AI contributes to the development of automatically detection or recovering fault systems. Okay, that is automatic fault detection is nothing but self system. Okay, so this self-healing capability is done by the incorporating AI. Okay, AI technologies. So this AI technologies are machine learning, deep learning, then the reinforcement learning, then expert systems, computer vision, generative AI. Okay, so the everything So so for prediction of tomorrow electricity demand based on the history of data that that is done by the machine learning. Then deep learning, it is also a subset of machine learning. It is networks. Okay, it uses AI and artificial neural networks to analyze this complex data. Okay, then it can also predict this solar or wind power generation using weather or environmental data. Okay, then reinforcement learning. It is also an AI technique. It is also used for finding the best decision. So expert systems, they are all types of AI systems which can be used for prediction as well as optimization of energy techniques. Okay. So this steps shows the step-by-step process or procedure of the workflow of machine learning. So first data acquisition, then data pre-processing, then model training, then validation, deployment, and continuous learning. Okay. So here is the workflow. So data can be acquired. So then it can be pre-processed. Okay, it can be pre-processed. Then data means data from the meters, smart sensors meters is collected. That is data acquisition, and then it is pre-processed and using some filter algorithms, and it is trained. Okay, so training is done, and then validation. So training, testing, then validation, then deployment of data. Okay, deployment means implementation. Then using real-time decisions, and it can further grid optimization and energy management can be studied. So this is the step-by-step algorithm of machine learning in smart energy systems. So next topic is load forecasting using AI. So load forecasting in the sense it uses this machine learning to predict this demand of electricity. Then this load forecasting is used for balancing power generation, then cost and reliability. Okay, grid reliability, then efficiency. So all the balance between power generation, cost, grid reliability, and efficiency is defined as load balancing. Okay. So there are different types: is short-term forecasting, medium-term, long-term, demand prediction, and then the three types of forecasting are there. Then some minutes, the precision, the forecasting or prediction, the minutes to 1 week. Okay, that comes under short-term forecasting. Then weeks to 1 year, and more than 1 year, or which comes to long-term forecasting. Okay. So this is the energy demand forecasting workflow. So it uses a bidirectional bi-LSTM algorithm. Okay, so this is a case study which uses. So it is a case study for identifying energy demand forecasting, and this bidirectional long short-term memory algorithm can be used often. It is a type of neural network that is you use this algorithm as a research for energy demand forecasting. Okay, so it's a good work to those for the scholars to going on their research. Okay, so first historical data can be analyzed from the power resources, and then based on the historical data, the actual power output can be generated. Okay, the actual power output can be generated comparing with the past data, historical data. Then training and testing can be done. Okay, before training, data collection is required. Okay, data collection or data acquisition is required. Then normalizing or the data can be done. Then the data can be related to training and testing. Then validation of the data can be done. Okay, so a model, the bi-LSTM model can be built. Okay, so actually it is a RNN network which is designed for continuous or sequential data prediction. Okay, so it can be used for both forward as well as backward directions. That is mainly this bidirectional smart grid systems. Therefore, this algorithm is efficient for predicting the energy demand forecasting. Okay. And finally, that validated model is evaluated, and the just like this mean absolute, then root mean, then this mean percentage error, then coefficient of determination of energy demand. These performance parameters can be evaluated by this by LSTM algorithm, and that can be compared with any other existing systems. Okay, so this is one of the research for identifying energy demand forecasting. Okay. So the next case study research is AI-driven smart grid system. So AI-driven smart. This is also the scholars can do the on this AI-driven smart grid system. So it is a smart grid system used for predictive analysis. Okay, it is used for predictive analysis. So it integrates artificial intelligence and energy management system or data management system to this electrical efficiency. Okay. This AI predictive analysis module, which has historical data prediction, which is compared with the real-time data, and this can be used for weather forecasting. Okay, forecasting, then energy distribution, demand, energy demand management, etc. Okay, so this is a good research work which is used in smart grid systems. So this is the of energy, renewable energy forecasting. That is solar power prediction. All the thing are what's okay. Some case studies which can be used for research works. Okay. Solar power prediction, then wind power, weather analysis, weather prediction, then grid balancing support. So this is another case study, like photoelectric solar prediction data from the satellite system. Okay. So the energy demand is shown in the diagram. Okay. So just giving the idea, and these works can be done very efficiently for research works. So this is the model I have explained already and used for wind power prediction. Okay. So historical data, and that can be compared with the real wind power. Both are given to the by LSTM model, and after training and testing, it is deployed, and the forecasting can be done. So what do you mean by grid balancing support? Okay. So the electric or smart grid must provide a constant balance between generation as well as consumption. Okay, so that is mean by grid balancing support. Okay, so here actually solar, wind power, everything will be fluctuating, and forecasting or prediction is essential. Therefore, AI comes into existence for the renewable generation, then electricity demands, then it backup the backup generator, then it controls battery energy storage systems, and it optimizes power flow across the grid systems. Okay, so these are all the involvement of AI in grid balancing support. So, okay, there should be a balance between the generation as well as consumption. Then only the demand of the consumers can be satisfied. So these are the main key benefits of smart energy operation systems. So we studied learned about predictive maintenance. So predictive maintenance is the maintenance strategy that uses AI or machine learning, which with the smart grid management systems. Okay, so that is predictive management system. Then already we go through fault detection and diagnosis. Then demand response management. Okay, that is the demand response. There should be a balance between the generation as well as consumption. Okay, then AI-based energy optimization. So then there is microgrids. Okay, microgrids means small DERs. Okay, distribution energy resources. That is microgrids as well as small utility centers. That is that is all beneficial by this smart energy optimization. Then AI, you are using AI techniques. Then sustainable automation is maintained. So automation for the present lifestyle as well as future. Then Industry 4.0 and smart energy, emerging techniques are adopted. Then this environmental and sustainability is also beneficial by the smart energy optimization methods. Okay, so these are all the advantages of smart energy optimization. So there are some certain challenges of in integrating AI. Okay, so the data privacy, how privacy of data is maintained. These are all again some research areas in the smart grid systems. Okay, energy management systems. Then the security of grid. So everything is in using the smart grid or AI autonomous grid systems. Okay, autonomous AI integrated systems. But again, and further we can do the research in these areas. Okay. So these are all some other challenges in AI smart grids. Okay, so what about the quality, operability, then visibility, regulatory issues, investment cost, everything. Then these are the emerging areas. Okay, emerging trends in AI for smart energy systems. Then digital twins, federated learning, then Edge AI, vehicle systems, that is V2G systems, then autonomous grid systems. Okay, digital twin is the recent technology, or it is the virtual automation system of or it updates continuous monitoring. Okay, so federated learning means it is also a machine learning technique. It is a machine learning approach where multiple are meters multiple devices or multiple organizations are interconnected, and which can share it can without sharing their data, the learning can be done. Okay, so traditional AI learning, the AI learning, the data can be collected from the source to the server to the AI model. Federated learning, there are different multiple devices which can give the data continuously. Okay, like a device A will give the data, device B will give the data. So many, there are multiple devices or multiple organizations can be interconnected. Okay, that is federated learning. Then to grid system. So this allows electric e-vehicles. Okay, it is a new technology. Which is used for bi-directional data system. Okay, it is used for charging of the e-vehicles. Okay, that is more automated systems, and it also adopted this AI, machine learning, IoT, edge computing, everything is adopted in it. Okay, that is vehicle to grid systems. That is nothing but normal e-vehicle to smart grid, everything with the AI technologies. Okay, autonomous grids. Okay, that is also advancements than the smart grid systems. So the main advantage of these all the systems are it can give good reliability of those grids. Then it gives more efficiency. Then increased customer demand can be satisfied. Okay. So this is the picture which shows the future of smart grids. Okay, so future of is nothing but which is adopted. Smart grids is adopted with the autonomous AI based grid system with the digital twin technology or federated learning, V2G systems. Okay, so edge AI, everything. So everything inbuilt to form the smart grid systems. Okay. So by integrating all these technologies, we will have a sustainable automation and highly efficient power grids, which is capable of sustainability and for large scale renewable energy resource systems for our future. Okay. Thank you. Thank you, dear participants. If you have any doubts on smart grids, you can ask me.
Thank you, Dr. D. Menaka, for the informative and insightful session. We truly appreciate the valuable knowledge and expertise you shared with us today. Now, I would like to invite the participants to share their feedback, comments, or questions regarding today's session. We shall now present a token of gratitude to our esteemed person in appreciation of her valuable time and insightful section.
Once again, on behalf of the Department of Electronics and Communication Engineering (CMAT), I extend our heartfelt gratitude to Dr. D. Menaka for taking the time to be with us and for sharing her expertise. We wish you all the very best in your future endeavors. Thank you, ma'am.
Thank you, ma'am. So one question is asked in the chat box. So how effective AI can be used in smart grids? Okay, I'm seeing now. Okay, actually, AI, effective AI means that is nothing but this autonomous AI system, autonomous grid systems. Okay, so the effective AI in the sense, I said though the emerging AIs, that is this V2G edge computing, then the even the emerging technologies. Okay, so computer vision, digital twin technologies. So these federated learning in the sense, it is the advance of machine learning. So these all AIs integrated together. It is in smart grids, which is called as autonomous 5G grid systems. Okay, so they will be efficient in give in and in what demand side management system. That is, they are they are actually working based on the demand of the consumers. So it is called. So we will say yes, AI is effectively used in smart grids. Okay, so it is mainly used for and bidirectional data monitoring system. The conventional grid system, it will be used only one directional flow, and the smart grid, which is adopted in smart cities, which is continuously used for bidirectional direction. Okay, thank you the organizers for inviting me to give a wonderful session on this smart grids and management optimization. Okay, thank you, Vinod sir, and the organizing team of this FTP again once again. Okay, thank you.
Thank you, madam. Thank you for the valuable and madam.
Thank you, ma'am.
Okay. Shall I leave the meeting?
Yes.
Sure, madam. We can finish the meeting.
Okay.
With this, we conclude today's session of the 6-day International Faculty Development Program on Smart Biomedical and Sustainable Electronic Systems, AI, IoT, and Green Technologies. I would like to extend our heartfelt appreciation to all the resource persons for sharing their expertise and to all the participants for your active engagement and support. We hope today's sessions have been informative and enriching. We eagerly look forward to your participation in tomorrow's sessions. Once again, thank you all.